Good afternoon, everyone, and thank you for being here. My name is Bohan, and I'm a PhD student at the University of Florida. This work I will present today is titled Towards Building Reliable Machine Learning Surrogates for Scientific Applications. Over the next 15 minutes, I will discuss why today's ML surrogate technique can be unreliable and how our framework here, which we call PALM, makes them both fast and reliable, fully automatically. Let me start with a little bit background of what an ML surrogate actually is. Most HPC and scientific applications follow the 80-20 rule. They spend the vast majority of their runtime instead of just a handful computational hotspots. The code on the left is such an example. A nested loop that is expensive to compute and has two labels to show, both time-consuming and frequently invoked. The idea of the ML surrogate is to take the hotspot region like this one and replace with a small neural network, showing on the right, that has learned the relationship between the input and output. So at the runtime, instead of executing the expensive original computation, we just run a faster forward pass to the network. Why neural network specifically? There are three major reasons. First of all, the architecture is simple to conduct, and secondly, we can directly trade accuracy against the computation by size of the network. And third, once the training finished, the same model runs on the CPU, GPU, and the FPGA through the standard framework, no rewriting. So surrogates give us both speed and portability at once. The natural question is, can we build this automatically with no expert in the loop? That's where the prior work comes in. Recently, several techniques have tried to automate the surrogate construction. The current state of art is called the AutoHPC-9, was published in the HPTC in 2023, which combines the autoencoder with the AutoML. These approaches are the real step forward, but they share the blind spot. They treat the target program essentially as a black box. They look at the data flowing in and out, but they ignore the code structure itself. And the structure is exactly where the reliability problem comes in. Our key insight, the program structure also matters, and we should analyze it. So we propose PALM, the Program Insight Analytical Driven Learning Model. The PALM insight both static feature of the code and the program's runtime behavior. And the use that to build the surrogate model are accurate, reliable, and still fast. Before I describe how, let me show you the evidence that motivated it. We start with an initial study to pinpoint exactly where existing surrogates break down. We assemble 11 representative benchmarks from the AXBench and Parsec suites, plus 2 large-scale scientific applications, a CFD fluid simulation, and the PureMD molecular dynamics code. As a baseline, we use the AutoHPC-9. The most important part is how we measure the quality. We use 2 metrics. The first one is called the MSE, but the second, and the one really matters, is called the failure rate. The fraction of the output which the final program output after the surrogate runs violated an application-specific quality of the interest threshold. It means whether the program as a whole still produces an acceptable answer. Let's look at what we found. This table shows the baseline across 11 benchmarks. Look at the 2 columns I have boxed in the red, the failure rate, and where the region have the branch divergence. And the result is frankly alarming. For Sobel, the MSE is essentially perfect. It's 10 to the -7, but yet the failure rate is 100%. And also the CFD tells the same story. And in the rightmost column, The 7 of the 11 benchmarks marked as a divergence, and those exactly high failure rate ones. So the headline takeaway is the low model error does not guarantee a correct program. A surrogate can fit into the data perfectly, but still wreck the application itself. So we investigate why and found 3 distinct root causes. I will walk through each of them. The first root cause is the branch divergence. Many target region contains the branches that lead to generally different computations. The code on the right is called the black shorts. 2 branches select by the conditional O type equal to 0. Here is the subtype part. The both branches return the same output, the option price, but is computed very differently. Branch 1 calculates the extra complementary variables that branch 0 never touches. Now, imagine the training just a single size one-fits-all network across the both branches. It forces to average 2 behavior and capture neither cleanly. Exact how failure rates come from here. And this isn't the corner cases. 4 of our 11 benchmarks have it. Pump fix it to recognize the branches and build a separate model for each of them. For the black shorts alone, that cut the failure rates from the 40.6% to the 6.6%. That's the first problem. The second one is more subtle. The second root cause is inconsistent interface variables. This is a compute flux function from the CFD, one of the dominant hotspots in the CFD. It has 3 branches, and critically, they don't even share the same interface input and output. The branch 0 and branch 2 output the 3 quantities: density, energy, and momentum, but real difference in the input interface variables. Branch 1 outputs only momentum physically. These are 3 different situations: an interior cell, a wind boundary, and a far field boundary. If you cover all 3 with a one fixed model, you will force to zero pad the branches that doesn't fit, and that's a padding is a poison. It precisely where the CFD reaches a 100% failure rate. Pump fix it with gives each branch own model and own correctly sets the interfaces. So nothing is padded. Let's brought the CFD from the 100% failure rate down to about 12. That's one more root cause. The third root cause is called the mismatch quality goals. The scientific code are full of convergence condition and threshold that checks the guarantee of the physically valid results. The Sobel example is on the right, has on the line 10. It clamps a wire pixel into the legal range, 0 to 255 here. The baseline surrogates have no idea of this constraint exists. So even with an essentially perfect MSE, it occasionally predicts the pixel just outside of the valid range. So a single out of range pixel corrupts the whole images. That's why Sobel 2 fails on the 100% failure rate. And the pump fixes to extract this condition into the code and bake them directly into the model as a hard bound on the output layer, so the network cannot produce the invalid value. For Sobel, it drops the failure rate from 100% to the 3.4. So these are the 3 problems. Now let's show how is our pumps put the situation together. This is the overall pump workflow in 2 phases: the offline construction on the left, the online deployment on the right. At the offline phases, we begin with the code analyze and the interface abstraction. We compile them into the LVMIR and and we run the control flow analysis to find all the branches. Then the data flow analysis on each branch to identify its interface input and output. Next is a dynamic analysis. Input fuzzing actually runs the program. This is tell us which branches are reachable in the practice and the runtime, and collect the input-output training pairs for each of the branch. Then we group the similar branches, and for each group build one surrogate model. Using the architecture grid search to pick the network and the physics-informed learning to enforce those correctness constraints. Finally, at the online phase, we plug the trained model back to replace the original code region. So, and the program runs faster. And I want to emphasize that this entire pipeline is automatic. Then the user only needs to provide the source code and target region. There is no domain expertise and no manual model tuning. So let's zoom into the two of the more interesting steps. On the left is the input fuzzing. We perturb example inputs, a small random variation within the valid range, and the physical constraints. And each perturbed input may exercise the new branches, so we keep fuzzing until the set of the discovered branches stop growing concretely, until 10 consecutive runs finding nothing new, and collect about 10,000 examples for each branch, so each model gets a rich training data set. On the right is a grouping. So why group them all? Because one model per branch is very wasteful. It blows up the training time and blows the binary with the dozen of the models. So we measure how similar in two branches are with the constant similarity score as shown here. Over the variable and operator of each branch's use, the branches above a threshold merge into one group and share a uniform model. The one hard row, the branches with the different output sets are never grouped because that will reintroduce the interface mismatch problem. So that's how the problem is built. Now let's see how well it works. For the evaluation, we focus on the 7 benchmarks that exhibited the branch divergence. The hard cases, for each, the PALM generates the model in the PyTorch. We compare them with the C++ LabTorch library, embedded with them with one application, and run it on the NVIDIA A100 GPU. So we look at 3 things: prediction accuracy, failure rate, and end-to-end speed up. So on the right, you can already see the accuracy, the predicted versus the actual of each benchmark across the 6 regression tasks at the point C, tightly to the y equal to x axis, and even for the heavily skewed data sets such as the pure MD, but the accuracy alone isn't the point. Let's look at 2 metrics that matter end to end. Here are the main results. The top chart is the failure rate. The red is auto HPC night, blue is PALM. On average, the PALM reduced the failure rate from the 40.6% to the 9.9%. And it looks like the case that completely broke the baseline, the CFD and Sobel, both at 100% failure rate and dropped roughly into the 12 and 3. Those are exactly the branch divergence and the constraint problem that PALM was designed to fix. The bottom chart is the speed up against the original code. PALM delivered an average of 3.32 times, up to 9.98 on the Black-Scholes, essentially the same speed up as the auto HPC night, within about 2%. So here's the bottom line of the talk. PALM matches the state-of-the-art work on the speed while being dramatically more reliable, and it's a safety net. Whenever as the input fails the quality check at runtime, we fall back to the original code for the input as well. So correctness is never compromised. Now let's wrap up. To conclude, existing ML surrogates deliver the dramatic speed up. However, they depend on the menu, domain-specific tuning, and they can be unreliable. PaLM is an automatic, domain-agnostic framework guided by the program analysis. By combining the static code analysis, dynamic input fuzzing, and per-branch group model construction. So, to handling the branch divergence, inconsistent interface, and the physical constraints. So, as a result, PaLM cuts the average failure rate from the 40.6% into the 9.9%, while pursuing up the 9.28 times speed up without the human loop. That's all my presentation. Thank you very much for listening.